Hello and welcome to another lesson of A-Level Physics. Today's learning intention is to use the natural logarithm in a physics context, and this is a direct follow-on from the previous lesson where we looked at the laws of logarithms. Today's success criteria is to recall how the exponential function and the natural logarithm are related, to evaluate logs using a calculator, and to verify if a relationship can be classified as exponential. So let's just do a brief recap about why we are bothered about studying logarithms and exponentials. Well, as you can see from the board there, exponential functions are very important when it comes to working with capacitors. Now, capacitors can be used for pacemakers inside hearts to help keep people alive. It's much more preferable to use capacitors for these things than other things such as batteries for a whole variety of reasons, but obviously analysing how they charge and discharge is important to making sure they operate effectively. We also use exponentials and logarithms to look at things like carbon dating in physics, which has got applications in history, and of course looking at the growth of a bacteria population in biology. So any function such as f of x equals 2 to the power of x are classified as exponential functions. The most common for exponential function is f of x equals e to the power of x, where e is a constant approximately equal to 2.718. Now you don't need to remember the value of e because that button on your calculator will actually give you the exact value. So when inputting this, use the actual value of e on the calculator. Now, a graph of f of x equals e to the power of x would be shaped as shown there on the board. Now, what is important to note is, of course, that it increases steeply, but also when x is equal to 0, then we're going through 1 on the y-intercept. So if you were asked to sketch that graph, that is what you would draw. Now, obviously, you may also look at exponential decreases on this course, and we're going to look at some examples of that today. A graph for f of x equals e to the minus x would show an exponential decrease, and we can see there that it is just a reflection in the y-axis on that occasion for the graph of f of x equals e to the minus x. Now let's consider another function then, this function here, ln x. Okay, now what we call that is the natural logarithm. Exponential functions and the natural logarithm are inverse functions of each other. Now what that essentially means is that if you take the natural logarithm of e to the f of x, then the ln and the e will cancel out with each other. We're going to look at some examples now where we're going to be using that law. So for that example question, the first one says simplify e to the power of ln 4. Now, because e and ln are inverse functions of each other, they do opposite operations, they will essentially just cancel each other out and give us the answer of 4. Now, likewise, for the next one, if we take the natural logarithm of e to the power of 9, then the natural logarithm and the exponential cancel out with each other, giving us a final answer of 9. Now this one's a little bit more complicated. Here we've got e to the power of 2 ln 5. Now we can't just cancel the e and the ln straight away because we've got that coefficient of 2 in the way. So we're actually going to refer back to one of the previous laws of logarithms that we looked at last lesson by raising that 2 to the, putting that 2 up so that it is 5 to the power of 2 as I've done here in the first bit of working out. That gives e ln of 5 squared. Now we can cancel the e and the ln to give us 5 squared, which is equal to 25. Okay, let's look at an example now that deals more with a physics context. Obviously, it was good to look at those examples in terms of getting some practice in using the law, but obviously now we want to see what it's used for. So, a sample of radioactive material initially contains 1.2 times 10 to the 20 atoms of the isotope. If the number of atoms left after 1000 seconds is 3.2 times 10 to the 18, then work out the decay constant lambda for this isotope using the equation n equals n naught e to the power of minus lambda t. Now, to begin with then, we want to rearrange this equation to make it lambda equals. And to do that, it starts off nice and easy. We can just divide by n naught. That gives us, of course, n over n naught equals e to the power of minus lambda t. So the next stage that we've got to do is take the natural logarithm to cancel out that exponential function, because natural logarithms and exponentials are of course inverse operations. Now if we take the natural logarithm of the right hand side, we also need to take the natural logarithm of the left-hand side. That means that we'll get ln of n over n naught equal to minus lambda t. Now the final bit of the rearrangement should be quite straightforward. We can of course times by minus 1 to put the minus on the other side, and we can divide by t. That gives us lambda equals minus 1 over t ln of n over n naught. Then we need to refer to the information that was given to us in the question. So it told us that the time was 1,000 seconds, so we'll be doing minus 1 over 1,000. Then we've got the natural logarithm, which is ln. When you're doing this on the calculator, make sure you're using ln and not log. And then, of course, we've got the value of n, and we've got the value of n naught. M naught was the initial amount, which was 1.2 times 10 to the 20. N itself is how many we've got left after a time of t, so that will be 3.2 times 10 to the 18. We then substitute those into the calculator, press equals, and that gives us an answer of 3.6 times 10 to the minus 3 for the value of lambda. Now, if a quantity does decrease exponentially, it will fall by the same factor in equal intervals. And we're going to look at what that looks like here in example number 5. So it says the graph shows how the charge stored by a capacitor varies with time when it is discharged through a fixed resistor. Determine if the charge decay is indeed exponential. Now this was taken from an exam paper. We can see that we've got charge in microcoulombs on the y-axis and we've got time in milliseconds on the x-axis. I would start off, because we want to actually prove that it's exponential, state what exponential decay actually is. It's exponential if it falls by the same factor in equal intervals. Now to do that, then we're going to need to look at how much it falls by. So initially at time equals 0 we've got 4 microcoulombs, and then later on at 50 milliseconds we've coming out with 3.2. So if we look at the charge after 50 seconds divided by the charge initially, we would do 3.2 divided by 4, which will give us a constant value there of 0.8. Now to verify if this decay is exponential, we're then going to check that it falls by the same amount, i.e. falling by a factor of 20% in equal intervals. So now let's look at t equals 100 milliseconds. That, when we read it off there, is coming out at 2.55. Obviously there might be some slight margin of error there, but you're allowed a certain amount of tolerance. So we do then the charge after 100 seconds divided by the charge after 50 seconds. So 2.55 divided by 3.2 equals 0.8. Now, just because we have two values that have shown that we've dropped by the same factor in equal intervals, in the exam we need to do it 3 times in case one of them comes up as a discrepancy. So we'll do it again for t equals 150 milliseconds, so we're using the next 50 seconds interval, and you can see that I draw on the graph again to read off the charge at a time of 150 milliseconds, and that of course is 2 microcoulombs. So when we do Q150 over Q100, which is 2 divided by 2.55, that comes out with 0.78, which of course isn't exactly the same as the 0.80 values we had previously, but it is close enough to verify that this decay is indeed exponential. Now don't just leave it there with those 3 values, you would then need to put a final statement to actually say that yes, this decay is indeed exponential. To verify if a quantity decreases exponentially, we could instead plot a graph of the natural logarithm. If a graph of the natural logarithm has a negative gradient and is linear, then that also confirms that the decay is indeed exponential. I've shown that there on the board on the right hand side. So what I would like you to do now for me, please, is have a go at 2 sets of questions. The standard demand questions are very important for those of you that haven't completed at least AS maths, and the high demand questions take those principles and put them into a physics context. So question number 1, we were asked to simplify each of the following, and the first one is ln e to the power of 3. So to solve that, we know that ln and e are inverse operations, and so they will cancel out with each other to give a final answer of 3. The next one is exactly the same principle. We have ln e to the power of minus 2. The ln and the e will cancel out with each other to give an answer of minus 2. Now here I've got ln 2e. What I would need to do in this case is split this up using the laws of logarithms. Remember, ln of xy would equal ln x plus ln y. So I split that up in exactly the same way to give me ln 2 plus ln e. ln and e will cancel each other out to give an answer of 1. So the final statement that we would need to give there will be ln 2 plus 1. If you wish to, you could on your calculator come out with a decimal answer for that instead. Part D, we've got e to the power of 3 ln 2. So we use the idea of bringing that 3 up to the power of the 2. So we get e ln 2 cubed. From there, of course, the e and the ln cancel out with each other to leave us with 2 cubed, which is equal to 8. Now for part E, we've got ln root e. Remember that root e is the same as writing e to the power of a half. So the natural logarithm in the e will cancel out to give us a final answer of a half. And then for part F, we've got ln 6e. Again, we'll split that up using the multiplication again. So we get ln 6 plus ln e. And then, of course, ln e is just equal to 1. So the final answer, in terms of the natural log, is ln 6 plus 1. But you could work out a final answer on your calculator if you wish to. Question 2. The decay of charge on a metal plate when it's attached to a discharge circuit obeys the following law. Q equals Q naught e to the minus t over RC. If Q naught equals 20 coulombs, R equals 5 ohms, and C equals 2 farads, then work out the time it takes for Q to become Q equals 10. So we'd start off then, we want to work out the time, so we need to rearrange this equation for time. So to do that, we will begin by dividing by Q naught to give Q over Q naught equals e to the power of minus t over RC. Now from there we take the natural logarithm of both sides to give ln q over q naught equals ln e to the minus t over RC, but of course conveniently the ln and the e will cancel with each other to give us the equation as written there. We now need to get t on its own, so we multiply by RC because we've currently got those being divided on the right hand side, and of course we can times by minus 1 as well to give t equals minus RC ln of q over q naught. We then substitute the values into the equation, so minus 5 multiplied by 2 multiplied by ln of 10 over 20 gives a final answer of 6.93 seconds. Question 3. Explain how a graph of ln of x can show that a quantity x decreases exponentially as n increases. Include a sketch of the graph to back up your answer. Well, we looked at this in the notes about 2 minutes ago. Of course, a graph of ln of x against n would show an exponential decrease if it is linear and it has got a negative gradient. They are the two conditions for showing exponential decrease on a graph of ln of x. Okay, now let's look at the higher demand questions. A student investigated a hypothesis. As the volume of a gas increases, the pressure of the gas decreases exponentially. We're going to determine if the student's results support that hypothesis. In other words, does the volume increase? As the volume increase, the pressure decrease exponentially. So we'll do that in the same way as before. We'll start off looking at the graph and choose a volume of 8 centimetres cubed. When the volume is 8 centimetres cubed, the pressure is equal to 20 kilopascals. Now that means then when we move on to 9 centimetres cubed, we can read off what the pressure is there, and the pressure will be 176. So we're using an interval there of 1 centimetre cubed, and so we do 176 kilopascals divided by 200 kilopascals, which equals 0.88. We would then pick another interval to do, so we can go up in another equal interval to 10 centimetres cubed. Now the volume of 10 centimetres cubed gives a pressure value of 160. Obviously you can have some slight margin of error for reading off the graph. 160 divided by 176 is equal to 0.91. Now because the ratio isn't constant, there is some variation there, we can say that the decay is not exponential. Then part B said, how could the students have presented their results differently to determine if the hypothesis was correct? Well, the alternative way would have been plotting a graph of ln of p against the volume, and that would have had a straight line but with a negative gradient. Then question 2, if the charge stored by a capacitor decays exponentially over time, Q equals Q naught e to the minus t over RC. If Q0 equals 50, R equals 200 and C equals 2F, then work out the time it takes for Q to fall by 20% or to 20%, of its original value. So the rearranging is the same as it has been for all of the others. We divide by Q0 and take the natural logarithm of both sides. But if we are falling to 20% of our original value, then the value of Q over Q0 has got to be equal to 0.2. So you could use, for example, 10 and 50 as I have done there, and the answer will come out as 644 seconds.